Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 94. It's on elastic and inelastic collisions. Let's say we take a ball that has 10 joules of potential energy, and then we simply drop it on a table. Now, it probably is not going to do that, but if it did, it would be a completely elastic collision. We converted that potential energy into kinetic energy, and as it bounced off the table, it returned all that kinetic energy back into the ball, so it was able to make it back again. Completely elastic. Now let's say we take another ball that is made of different material, drop it. It also has 10 joules of energy, but it doesn't bounce at all. We would call that a completely inelastic collision. Now where did that energy go? Where did those 10 joules of energy go? They became internal energy in the table and the ball itself that collided. Now we know that most balls are going to be somewhere in the middle, somewhat elastic in their collisions. And so during any collision, which could be elastic or inelastic, we're going to maintain linear momentum. In other words, the momentum of the objects before the collision is going to equal the momentum of the objects after. In an elastic collision, not only do we maintain linear momentum, we also maintain kinetic energy. The speed before the collision equals the speed after the collision. Again, it's rare that that's going to occur. In an inelastic collision, we still maintain linear momentum, but we've lost some of that kinetic energy. Where did the energy go? It became energy, internal energy into the objects themselves. And so let me show you a collision between some Matchbox cars. Okay, so we saw two collisions there. And so one of those is elastic and one of those is inelastic. Did you figure out which one? So we call that an elastic and this an inelastic. So in an elastic collision, we maintain all of that kinetic energy. In an inelastic collision, some of that energy goes into the internal energy of the objects itself. If you think about two real cars running into each other, there's a lot of damage done inside those cars, and that's internal energy. It used to be kinetic energy that is doing the damage inside the car. Let's start by studying some elastic collisions, and we're using a SimBucket simulation where carts will collide with each other. You can see on the left side that we have a 1 kilogram cart. Is traveling at 5 meters per second. That means it's going to the right. And then we have a 1 kilogram cart that's traveling in 2 meters per second to the right. And they're going to bounce off of each other. And now we have some new velocities after that collision. And so was linear momentum maintained? Well, it's always maintained in a collision, but let's study that. If we look at the conservation of linear momentum, P1 plus P2, in other words, the momentum of those two objects before has to equal the momentum after. So M1V1 plus M2V2. So if we were to say M1 is 1 kilogram cart going at 5 meters per second, and then a 2 kilogram cart going at 2 meters per second. So this is the momentum before. Does it equal the momentum after? Well, if I multiply that out, it's 9 kilogram meters per second on both sides. The positive value indicates that the overall momentum of the system is towards the right, but it's equal, and it always will be equal in every collision. But did we maintain kinetic energy? To do that, we're going to have to use a different formula. Kinetic energy in has to equal kinetic energy out. This is an unwieldy formula. And so again, it's just 1/2 mv squared. That's kinetic energy, remember. This would be of object 1 and 2 before and then after the collision. So if I plug in those values here, what we find is that the 16.5 joules we had before the collision equals the 16.5 joules that we had after the collision. This is an elastic collision. They're just bouncing off of each other. We're not losing any of that kinetic energy. But let's say we deal with an inelastic collision. Remember, in an inelastic collision, in this case, let's say it's completely inelastic. These two carts are going to come connected to each other when they collide. Then this formula, conservation of kinetic energy, is useless to us. It doesn't help us at all. But what's neat is since they have a shared velocity after they collide, we can use the conservation of linear momentum to figure out, where's that energy going? And so if we write it out like this would be momentum before and then momentum after. You can see that in this case, those two carts are going to become connected. And so the velocity of both of them after is going to be exactly the same. They're going to become connected. And so I've written that as V3. This is our new shared velocity of the two. And so what I can do is I can plug in my values. We had a 1 kilogram cart going at 5 meters per second before the collision and a 2 kilogram cart going at 2 meters per second after. The masses don't change And so I can solve for that v3. I can solve for a velocity of 3 meters per second. And so if it's an inelastic collision, since they're connected, that shared velocity allows me to solve for the change in linear momentum. Let's make sure that that works. Yep, they both have 3 meters per second that's going to the right. And so did you learn to predict the outcome of either an elastic or an inelastic collision? Remember, elastic is when we don't lose any of that kinetic energy. Could you plan data collection? I'm using a simulation, but you could use carts colliding as well. Did you learn to classify a collision as elastic or inelastic? If we lose that energy, then it's going to be inelastic. And then finally, could you apply the conservation of linear momentum to an instance where we have an inelastic collision to solve for its final velocity? I hope so, and I hope that was helpful.